everyone, and welcome to the Interagency Modeling and Analysis Group pre-meeting webinar series for the workshop on integrating machine learning with multiscale modeling. And we are pleased to have folks from NASA here on this recording, and I will introduce Dr. Jerry Myers from NASA to introduce our speaker.
Hi, everybody. As Grace said, my name is Dr. Jerry Myers. I'm from the Glenn Research Center in Cleveland, Ohio, working for NASA. Well, today you're going to hear some of the work that we've been promoting using machine learning to help aid us in advancing our healthcare abilities for astronauts. And Dr. Alexander Cheppelman, or Alex as we like to call him, is going to be giving you a talk on some of the very interesting work that he's been doing in bone mineral density maintenance, as well as some overviews of the other applications we have for machine learning. Alex, take it away.
All right. Well, thank you very much for the introduction, Grace and Jerry. As Jerry said, I'm Alex Cheppelman. I'm a robotics and computational modeling engineer at Zinn Technologies. We're an aerospace contractor that does a lot of work with NASA Glenn and some other companies. And one of the things that we always are interested in helping with is NASA's Human Research Program. So just briefly about me, my history started in 2009, where I was a graduate student at Case Western Reserve University. There I worked on an autonomous lawnmower called Crew Cutter, and was primarily responsible for the real-time computer vision and control. And then I moved on to Carnegie Mellon, where my research shifted more towards human robotics and prosthesis applications. Specifically, my project involved building a dynamically scaled locomotion test bed that could be used to evaluate swing placement controllers for prosthesis applications. And as part of that work, then I moved on to developing nonlinear springs for improved force sensing in the robot's actuators. That led me to a postdoc position, also at Carnegie Mellon University, but at a different lab, the Biorobotics Lab, and one of their spin-off companies to help commercialize one of their modular series elastic actuator designs. And then that work finally led me to Zinn, where I'm now currently involved in some robotics and computational modeling work, which I will be speaking about today. So much of the work that we do for machine learning falls under the Cross-Cutting Computational Modeling Project, which is led by Jerry Myers here from NASA Glenn. And CCMP is located within NASA's Human Research Program. And essentially what CCMP tries to do is to try to fuse traditional research with computational modeling to better characterize risks and improve decisions making for human spaceflight. So hopefully being able to make sure that spaceflight becomes safer, and then eventual missions that we have to the moon and Mars both go off without a hitch, but then also allow us to return the astronauts that we send there safely there and then safely back to Earth. Within HRP, machine learning is currently used in areas primarily related to in-flight, in-mission, and long-term medical risk assessment. But since kind of those initial applications, we've also been branching out to apply machine learning in order to investigate unique health and performance concerns and specific human physiology changes during spaceflight, one of which is this bone project that I'll be speaking about today. So it turns out that long-duration spaceflight and long-term microgravity exposure is really bad for you. Essentially, when astronauts are in a microgravity environment, they can lose between 0.4 to 2.7% of monthly bone volumetric mineral density during these missions. And that's problematic both because it poses an in-flight risk and in-mission risk when an astronaut might break a bone in space, but it's also problematic when astronauts return to Earth because some research shows that some of the volumetric bone mineral density lost during spaceflight is never fully recovered. Additional research has shown that resistive exercise can counter the effects of microgravity, but because every person is so unique and just in general has different needs in order to maintain their bone mineral density, the required exercise frequency and the duration of that exercise that an individual must perform is unclear. Towards that end, NASA has been working on developing these personalized computational models that may provide insight into the required amount of exercise that a person needs in order to maintain bone mineral density. And specifically, one idea that we've been investigating is to create the subject-specific bone finite element models from astronaut CT scans, which we can then fold into the loop with these computational models to hopefully be able to determine the amount of exercise that a person needs to maintain their bone mineral density. One of the issues, though, is that it is very time-consuming to process these CT scans manually. So essentially, the way this finite element model creation works is that you take a CT scan of an astronaut, and then you can try to do some image processing, or in the worst case, go and hand label individual pixels in these CT scan cross slices to identify different parts of bone, and then use that to essentially build up a multi-material finite element model. The issue there is that per subject, for one bone, this process can take up to 10 hours or more. So certainly that is an issue if you need to try to turn these scans around quickly, especially if you want to update scans of an individual, for example, to see maybe how their bone geometry changed during microgravity or during space flight or during another event. What we were interested in seeing is to see, as part of this, was to see if machine learning can be applied to process these scans automatically. And specifically, one approach that we investigated is Bayesian classification. And essentially, the way this classification scheme works is that given an image, you can then come up with a bunch of descriptors for what a pixel means. So for example, maybe what is the average intensity, or what is the color of its neighbors, or how strong, if you run an edge detection algorithm, is the edge of one pixel compared to another one. And then what you're able to do is, using these Bayesian classifiers, basically calculate the conditional probability that a sample belongs to a certain group. So for example, a pixel that doesn't contain bone, a pixel that contains cortical bone, which is the harder outer shell, or if a pixel contains trabecular bone, which is kind of the spongy inner bone. And then using those statistics and those descriptors in aggregate, automatically classify whether or not a pixel is no bone, cortical bone, or trabecular bone. What we found is that using some training data from an individual, we were able to actually successfully identify bone-containing regions in an image, especially within a region of interest, with minimal post-processing, and we're able to generate this finite element model that you see here in the lower left, using a CT scan that you see up there on the upper left, and basically cut that time down from about 8 hours when it's labeled by a subject matter expert to about 10 minutes. So that was exciting for us. So now that we have a finite element model, we wanted to next fold that into this computational remodeling model that NASA had developed that relates volumetric bone mineral density to loads induced by individuals exercising. And essentially the way this model works is that it's a numerical model that models chemical remodeling rates as they are related to the aggregate daily bone strain that results from exercise. And the specific research that we're using to couple those two things together is a paper by Frost, and that's his mechanostat theory. And then using this mechanostat theory in conjunction with in-the-loop finite element analysis, we can then calculate the bone strain that is induced into bones for specific exercises, and we then calculate a quantity known as the daily load stimulus, which is a relationship that relates the induced single-cycle cortical and trabecular stresses that an individual experiences in bone to the frequency and the number of exercise repetitions that a person could perform. So in theory, what this will allow us to do is to essentially model the effects of individual exercise as well as the number of repetitions and the overall duration of the exercise to see how that relates to aiding in the maintenance of bone mineral density. With this model and with this in-the-loop finite element analysis, we of course needed some data to evaluate how well the model works. And for this, we used data that came from a 70-day bed rest study that serves as a spaceflight analog. Subjects in this study performed exercises that were consistent with NASA's Integrated Resistance and Aerobic Training Regimen study. And essentially that exercise regimen is designed in order to try to maintain an astronaut's bone mineral density for a certain period of time while they are flying in space. At this point, though, because there were several exercises in this regimen, we did not actually model the effects of individual exercise. Instead, we decided to first kind of lump all the exercises together into this equivalent kind of exercise that kind of civilians do or non-astronauts do, which is essentially just walking around on Earth for about 5,000 steps per day and seeing if essentially the forces that our model would predict in order to maintain bone mineral density matches those of forces that would be seen from individuals walking around. Specifically, the loading data that we got for kind of these Earthbound subjects came from a database called OrthoLoad. And this database has an instrumented hip implant, essentially, which measures forces in the X, Y, and Z directions. And then using those forces, essentially, what we wanted to check with our model would be two things. One, we wanted to see if using a stochastic optimization routine, the forces that the model needed in order to match these post-study BMD values was equivalent to that you would get from walking 5,000 steps per day. And then the other thing that, of course, we wanted to see with this model was whether or not the model was actually able to match the post-study bone mineral density at the conclusion of subjects at the conclusion of the study. And what we found was interesting. So for control subjects, which did not perform exercise, we found that the model was actually able to predict the post-study cortical and trabecular bone mineral density with a relatively small mean percent error across all subjects. So cortical VBMD was predicted with an accuracy of about 0.61%, whereas unloaded trabecular VBMD was predicted with an accuracy that differed by about 10%. Similarly, for loading, we found that when finite element analysis was folded in the loop with these models, the model was also able to predict and really accurately estimate the volumetric bone mineral density for subjects at the conclusion of the study, but we found overall that the forces that the model predicted in order to achieve these post-study values were significantly lower than those that we would see from the OrthoLoad database in many of the cases. And essentially, what we believe this results from is that kind of from two factors. One is we only used a single set of remodeling model parameters, as well as only one finite element model, which was unfortunately all that was available to the study. So that's certainly something that we're hoping to look into in the future with additional data. What we're hoping is to be able to get not only CT scans of individuals, but then also be able to use optimization in order to tweak these values that we need for these remodeling model parameters on a subject-by-subject basis, and then use kind of a machine learning approach such as Gaussian process regression in order to predict subject-specific parameters that we might need to fold into the model and use in the model to enable more accurate predictions. And the other thing that we did not incorporate in this model, which is suggested by literature, is that as you are in a microgravity environment, your bone geometry can also change. So certainly that's something that also warrants further study on that with additional data, at the very least pre-study and post-study CT scans, we hope to also be able to capture in this model. In the meantime, while this research is ongoing, this model and this information is also being used to inform the design of ATLAS, which is the advanced twin lifting and aerobic system that we're developing at Zinn Technologies with NASA Glenn. And the purpose of this device is that it's meant to be a general purpose robotic exercise device that can be flown on the ISS or eventual missions to Mars. And this cable-driven robotic exercise device can emulate a variety of different types of resistive exercise devices that you might find in a gym, for example, like a squat rack or a rower, or allow you to do curls. So hopefully that with a single device, eventually astronauts will be able to get kind of a total workout kind of within a device that just takes up relatively small volume on the spacecraft. So at this point, that's all I have for the presentation. Thank you very much for listening. And of course, if you have any questions, please let me know.